In this video, I will explain about exponential damped sinusoidal signals. So, exponential damped sinusoidal signal. See, the damped signal means its amplitude is approaching zero as t increases. Okay, somewhere at some point it will become zero. Okay, that I may consider it as infinity. So as t approaches infinity, our amplitude it starts to decrease, and as it approaches infinity, what happens? It will be zero. So in my one of the videos, I had explained you about the exponential signal, where it was represented as x of t is equal to c e to the power of at. So when a is equal to 0, we had a constant signal. When a is less than 0, we had decaying signal. And when a is greater than 0, okay, it will be the growing signal. So we are interested in this now, a less than 0, because what happens? This will be the graph for that, right? This was our exponentially decaying signal. Okay, so this exponentially damped sinusoidal signal, I can write this as x of t, that is equal to e to the power minus at sine omega t. X of t is equal to e to the power minus at cos omega t. Okay, here in both the cases I will consider a greater than 0. That means I am taking this part to explain. Okay, I am considering this part. See, sinusoidal signal, actually sinusoidal signal is like this, right? This is the sine signal. But now it is multiplied by this e to the power of minus at, which is an exponential signal. Now I can write this. Okay, this is your damped signal. So you can see the amplitude. This was your initial amplitude. Then what happened? The amplitude, it started to decrease, and as t approaches infinity, it will reach the magnitude 0. It becomes 0. Okay, this is your exponential damped sinusoidal signal. If I write it in terms of cos, it will be like this. Okay, so this will be your exponential damped sinusoidal signal. You know, this is the waveform for cos, right? This is the waveform for cos. Now this is in terms of sine, this is in terms of cos. See, if you see the peak, these are the peaks, right? If I see the amplitude, if I draw a line like this, okay, between the successive peaks, okay, this will be your peak. So it is following this exponential decay curve, right? So this envelope, outer envelope that is between the successive peaks is nothing but it is the exponential decay curve. Exponential decay curve. See, here also we can write it. This is your exponential decay curve. What is? It is the outer envelope of this signal. Then, in general, we can use one equation for that. Okay, that will be x of t is equal to a e to the power of minus at cos omega t plus phi. X of t, that is equal to a e to the power of minus at sine omega t plus phi. This I can write it in general, where phi is the phase shift. This one will be your phase angle. This one will be your amplitude. Okay, that is the amplitude. This will be your decaying factor. Okay, this is the decaying factor. You can also write it as e to the power of minus lambda t also. For an example for this exponential damped sinusoidal signal, we can consider a bouncing tennis ball. That means if I drop the ball, if I have a tennis ball, if I drop it from a height h, if I consider this as a height h, and if I drop a ball here, what happens? It starts to bounce, right? It starts to bounce, but it will never reach this height again, because it loses its energy. It starts losing its energy, and finally what happens? It will be on the ground after some time. So that also will be following the exponential decay curve, the bouncing tennis ball. Okay, so this is all about your exponential damped sinusoidal signal.